Welcome back. This is the second and probably the final segment for section 4.3. There's not a whole lot to talk about because the graph of cotangent is relatively, is quite a bit similar to tangent, and there's not a whole lot of new stuff there other than maybe the task of actually taking an equation, producing a graph, taking a graph, producing the equation when it refers to cotangent. So I previously started this segment, and in the middle of it, I had kind of a snafu occur. So I have the first page already. I restarted and I have the first page already written up. So you won't see me actually write it, which means I'll go probably a little bit faster. But here's the idea. Previously, when we were looking at a function that we had never seen before, we start by kind of plotting points and take a look at what, using some intuition about whether it's increasing or decreasing, produce the graph. But what we're going to do in chapter 5 is we're going to start looking at the relationship between all these functions using fairly sophisticated identity work. And so this is kind of a preamble to that. I'm going to start with, I'm going to use both the cofunction identity and the symmetry identity to produce an equation that will kind of show us exactly how cotangent is related to tangent in a pretty meaningful way. So let me switch over here to my document camera, and as I said, I've already got the first page of notes produced. So it's I'll try to be consistently a little bit slower just so the ideas develop properly. So this is section 4.3, page number 4, as I recall. And so I want to start with cotangent of x. Now, recall there are two well, there's an identity that we have that directly relates cotangent to tangent, and that is the cofunction identity. So the cofunction identity tells us the cotangent is equal to tangent of pi over 2 minus x. Now, that's in radians. You probably recall it as being 90 minus x from previous discussion, but we've moved on to radians, and so those two things are equivalent statements. So there's our cofunction identity for relating cotangent to tangent. Now, this is going to give us a little bit of issue because we've generally speaking, when it comes to graphing, we're always looking to have b be a positive value. But in this case, b is actually -1, right? If we rearrange this and said negative x plus pi over 2, you'd say, well, there's the negative b value. So what we're going to do is we're going to actually factor that -1 out, which is just an algebraic step. And as you can see, there it is right there, where we factored out a -1. So both of these will change sign. So it becomes positive x, negative pi over 2, and the -1 comes out. So remember, at the beginning, in section, I believe it's 4.2, maybe 4.1, we discussed the idea of symmetry of these functions, these trigonometric functions. And I said at the time that tangent is an odd function. Now, if you go back and look at your notes of what the graph of tangent looks like, it should be fairly obvious that it is in fact an odd function. But I stated it without any sort of proof, and there you have it. But basically what that means is that if I have tangent of a negative something, right, whatever that something is, it doesn't have to be x or theta or anything else, just whatever's inside that parentheses, negative times the parentheses, the negative sign will pop out of the equation, will pop out of the function and sit out in front. And so this is the next step. This is a symmetry identity where that negative sign comes out. And so now I want you to kind of look at what we have there. We have that cotangent is equal to negative tangent of x minus pi over 2. So what we have here, and if you just ignore the cotangent for a second, if you were to graph just this, it would be tangent, not translated vertically because d is 0, reflected without a vertical stretch, shifted to the right by pi over 2. So reflected, shift to the right. That's really all that happens. And so I did graph this previously, and so it's going to I'm going to give you a moment to digest it because I've already graphed it. So notice, I'm going to point out some salient features here. Since the normal origin of tangent coincides with the origin of the xy plane, if you shift it to the right by pi over 2, you would expect that reflection point to occur at x equal pi over 2, right? So, and then because the b value is still 1, the normal period for tangent is actually the period of this function. So nothing has changed about the period. So if we go half a period to the right, we have pi over 2. Full period, half pi to the right, we have pi. Full period to the right, it's 3 pi over 2. And if we go backwards, you'll actually have this vertical asymptote at 0. So because the d value is 0, the x axis will fall right in line with these reflection points. And because this vertical asymptote occurs at x equals 0, the y-axis will be sitting right on top of it. So the origin for cotangent is coincident with the vertical asymptote. Now, the only thing left to sort of put together is that at these quarter points, rather than being an increasing function, which it would be normally, because we have a negative sign in front of it, it's actually a decreasing function. But the values, the sort of quantities, the absolute value hasn't changed. And so this first point occurs at +1, and the third quarter point occurs at -1. So this, what we have sitting here, is the graph of cotangent. So I want to point out something that's kind of interesting, and really one of the main reasons why we do this sort of stuff is that we produced a graph without plotting without having to create any kind of point table. And that's really the goal. In college algebra, you spend a lot of time looking at whether functions are increasing, decreasing, where that happens, zeros of the polynomial, so that you don't end behavior, those sorts of things, so that you don't have to plot points all the time. And this is an example of that, because we just simply took a graph of something we already knew, we made some modifications to it, now we have the graph of something different. So what I'd like to do is I'd like to create sort of a generic cotangent function, and we will extract the AB, well, first off, I'll produce a graph, an equation, and we will try to graph it based on these, based on our translation, transformation properties. And then I will come back and I will start with a graph, and we'll try to extract the ABC D value and then write the equation for it. So those are the two main tasks that we're trying to achieve. Equation to graph, graph to equation. And as I said previously, I screwed up, and this is where I actually screwed up, because I did them out of order and then I messed one up pretty hard. So 4.3, I believe we're now on page 5. Let's start with an equation. How about y equal to 3 times cotangent of, let's make it x over 2 plus pi over 2, and then plus 1. Okay, so unlike sine and cosine, we have to be really cognizant of the SIGN on the A value. If it's negative, there really is something that substantively happens. But since this is positive, no big deal. We can just start by drawing the basic shape of the cotangent function, and I'll go ahead and, just so I keep things from getting a little too squirrely, I'll go ahead and put in these vertical asymptotes. And this reflection point occurs right in the middle. If we go over a quarter, there's my quarter point. And if we go back this way, a quarter, I'll replicate these points over here in the next period so that I have a graph that isn't totally garbage. Not exactly the same. Tangent and cotangent are a little bit harder to graph, honestly. And like I've said previously, I don't expect y'all to be artists. But to these 3 points and their location is pretty critical to being able to graph effectively. So let's first note, now this is, remember I was saying that there's kind of a trick that occurs every time you have a non-unitary B value. The book always puts it this way. And you kind of need to factor out whatever the B value is. So just as kind of an aside, I'm gonna write the factored version of this. So y is equal to 3 cotangent of 1/2 x plus pi plus 1. That's the fully factored version of this. So what that tells us is that the period has doubled, right? B has gone down, so the period has gone up. Maybe I should kind of write that here. Note P is equal to P naught divided by B, which is the normal period of cotangent, which is pi, divided by 1/2, which equals 2 pi. And then the corresponding things we can figure out. So remember that for cotangent, or sorry, this, I have this drawn as a tangent function. Let me just, rather than redoing this all, let me fix it. I'll put this negative sign in there. And correspondingly, here's a negative. So now I have a reflected cotangent. Sorry about that, but I figure it's not worth it to do this all over again. Okay, so it's a reflected cotangent that has the difference between the reflection point and the quarter point should be 3. But recall that now that we have this in the form where we have A, B, C, and D, that the quote normal origin for cotangent will be at the value CD. So the normal origin of cotangent is coincident with a vertical asymptote. So it's not even on the graph, but we could just say pick this one. So there's our vertical asymptote, but the y value is the same as the reflection point. So this coordinate is C, which is negative pi, D, which is 1. Right? Okay, and the period is 2 pi. So this next point over here, if we add 2 pi to this, will actually be pi, comma 1. Going backwards, this will be negative 3 pi, comma 1. So where does that put this reflection point? Well, it's halfway between. This is actually 0. And so since the x value is 0 at this reflection point, that means the y-axis has to go right through that point. Okay, so we could probably label a couple more points. It's not really critical what the x value is, but note that the y value of this quarter point is going to be whatever the y value is at the reflection point minus 3, because this distance between these two is 3. So if you subtract 3 from 1, you get negative 2. So this sort of corresponds to, let me write it this way. It doesn't really matter what the x value is, but the y value is negative 2. And so from that information, here's a y value of negative 2, here's a y value of 1. The x-axis must go somewhere in between them, and 2/3 of the way up. And so there's our graph. Now, to finish this out, we would probably put some labels on the actual axes. So this would be, we could call this one, say, 4 and -4. We could label maybe pi, -pi, -3 pi, something like that. So we have x coordinates, y coordinates, the graph in place with the vertical asymptotes. Now these coordinates of these points, just so we're clear, are not sufficient to produce the graph. They're kind of scratch work that I put on there so I could figure out where to put the axes. Now, one thing that I hadn't mentioned before, maybe I did, is that most people, when they first start graphing functions, they will try to just slap the axes out there sort of willy-nilly and start labeling them, and then they come in and graph the equation. And that often creates graphs that are pretty terrible because the actual function may be far off to the important features may be far away from wherever the origin is. So what I always recommend is to graph, put in the graph sort of the shape of the function first, and then place the axes and their labels in that order. So first graph the overall feature, which we established because it's a reflected cotangent, has this increasing sort of S curve to it, constantly increasing. The vertical asymptotes are put in place. That's the graphical features. Then the axis is put in by identifying some critical points and establishing where it has to be. So this is sort of backwards from what most people do, but it is actually the most effective way to get the important features right smack dab in the middle of your graphical space. Okay, so let's try taking a graph and producing an equation. So let me start by, I'll do one that's not reflected this time, but I will start by producing the vertical asymptotes. And since it's a cotangent, I'm going to go ahead and put in the 3 points. So let's put we'll make it a little shallow here. So quarter points, and then I'll replicate them over here. Just makes for a better graph when it's all said and done. And now, kind of finish it out, that S curve. And now let's establish a location for the y-axis. I'll put it so it's coincident right with this quarter point, so it's a little bit easier to work with. So I'll make that the y-axis, and I'll put some. Let me put some numbers on it. Let me make this. Well, I'll put the x-axis down here somewhere. Now to put the labels on, I'll make this, let's say 4 and 8. And then to put some labels on the x-axis, let me make this 3 pi over 8 and 7 pi over 8. So if we wanted to come back and put this one in, it's actually negative pi over 8. Okay, so what we need to do is we need to establish A, B, C. In order to write the equation, we need to establish A, B, C, and D. And as I've suggested previously, the way to do that is first find C, then C and D, then B, then A, in that order. You can kind of interchange them, but I find for myself that that's the easiest way to do it. So looking at the graph, we want to identify the feature that corresponds to the quote normal origin of the cotangent function, and that is the first vertical asymptote is normally coincident with the y-axis, and so therefore it is the origin at the origin, and where the reflection point occurs. So if we just sort of right here, if we can figure out the coordinates of this point, then we have C and D. So the reflection point is halfway between 4 and 8, so the y value is 6. And of course, we have the x coordinate sitting there right in front of us. So this is 3 pi over 8, comma 6. And these will be the C and D value. Similarly, so this, we'll get from this, we'll get the C and D. Now, to get B, remember we have to look at the period. So the actual period is the distance between successive asymptotes, which in this case is 7 pi over 8 minus 3 pi over 8, which is 4 pi over 8, which reduces down to pi over 2. So maybe I'll just, yeah, we'll pull that later. And then finally, the distance between the point of reflection and either quarter point will tell us what the magnitude of A is, what the absolute value of A is. Because this is not reflected, A will be positive. But the distance vertically from that reflection point to either one of these is actually 2, which tells us the A value is, the absolute value of A is 2. Because it's not reflected, the actual value of A is positive 2. So I'll kind of summarize those down here. So CD is equal to 3 pi over 8, comma 6. The period, the B value is equal to the normal period divided by the actual period, which happens to be pi over 2, which reduces down to just 2. And then A, simply by inspection, is 2. So now to put that all together, we have y is equal to the A value, which is 2, times cotangent of the B value, which is 2, times x, minus the C value, which is 3 pi over 8, plus the D value, which is 6. And notice this is the fully factored form, but you might want to do something with that. I don't know. There's alternatives. This is usually kind of the easiest way to do it because all of the graphical features can be extracted pretty easily. But this happens to be exactly equivalent to 2 cotangent of 2x minus 3 pi over 4 plus 6. They're the same thing. Okay. So this is sort of all the tasks that we will need to do with tangent and cotangent for this chapter. To be quite honest with you, and I'll just kind of ramble on here a little bit. There are very few physical phenomenon that can be modeled with a tangent or a cotangent graph. So this process of taking a graph and producing an equation is really more academic than practical. I mean, I suppose there are maybe some situations in circuitry or whatever that occur, but the issue is that, you know, some physical feature, what a physical phenomenon, which would be correspond to the y-axis, has to blow up to infinity, and that isn't realistic. But maybe there, you know, aside from where it actually blows up, maybe we're looking at a certain piece in there where we have this sort of reverse curve where maybe that's an appropriate model. So the full-blown tangent or cotangent graph just doesn't really occur in nature. So that as I said, it's more of an academic concern. Okay, well, that's this ends section 4.3. I will see you again in 4.4.